Alright, so this is an update of the 65 CO2 computer that I've been working on. It's changed a bit since the last video, which I think we made in April. I've changed the way that the parallel or the input-output works. So I have a 65C22 VIA in place of the latching system I had before. I switched to using the Atmel EPROMs, which don't require multiple voltage levels, so they're easier to work with. Replaced the old CPU with a genuine WDDC 65C22, and added a few more auxiliary functions here. These are dual 7400 NAND gates for instruction decoding, phase correction, and this one's actually not connected right now, but it's supported with modules now. So I have here the module for an LCD screen, which is able to take the input-output port and convert it into something that is readable by an LCD like this. There's also a buzzer underneath there and some transistors for power control for the LCD. And these just plug straight into the board here. If I hit the NMI reset, it will initialize the screen like normal. It still uses the Arduino to send the timing output to the CPU, the VIA, and the phase correction for the RAM chip. But without changing any of the functionality from the last video, by optimizing the code on the Arduino a lot, I was able to get the output clock signal from about 200 kilohertz in the last video to about 1.6 or so megahertz on the output. So for example, the output waveform without any optimization at all from basically where it was the previous video looks like this. Whereas with some optimization, it looks like this, which is about 800 kilohertz. But with full optimization, including changing the compiler settings, it's up to this. Using the VIA, I've been able to create several other peripheral devices that can connect to this computer. One of the previous projects was getting VGA working. So in this case, I had a breadboard set up with an ESP32 and was driving a VGA display with it. And it did work pretty well, and I was able to actually get console output for the computer, but it kind of takes up a lot of space and doesn't really run that fast. In this case, I'm currently working on a teletype system using an old typewriter. For this, I created a controller that is wired in directly to the controller for this typewriter. So if I pull this out and flip it over, you can see that the wires from that are going underneath the board and are soldered onto the address and control pins of this chip right here. In order to get this to work, I took out the controller for the typewriter and soldered my controller directly onto the scan code and address of the demultiplexer and the input for the keyboard. Now I'm currently loading over a version of Forth that uses a special routine to connect to the driver of this printer right here, this typewriter. So I can turn this typewriter on. It'll start initializing. The data is sent through parallel, and it's latched in by the end bit here because ASCII only uses 7 bits. The 8th bit is used to actually latch the data. So now this is loaded over, I can run the version of Forth that basically redirects the output from the serial to the quote-unquote teletype here. So I'll go ahead and run the program. So in my version of Forth, everything is interpreted. There's no compiling mode. So here I'm writing a small program sped up, and it's just going to print out some stars. So I might go more in depth on how this works in a later video, but for now I'll link the GitHub to the typewriter code down here. I'll probably make another video also explaining all the software that I've written. I've completely rewritten the monitor and added a lot more software that hasn't been there previously.